Professor, I'd like to begin with the family into which you were born.
Well, I hope you can call me Avi, because everybody does.
Avi,
Yeah.
Tell me about the family into which you were born.
Both my parents are Holocaust survivors. And they're among the very few of their families that survived. They met in Israel. And my father was an electrical engineer, worked for the Navy. My mother was a nurse part-time. We grew up, me and my two brothers, in a tiny apartment in a blue-collar neighborhood on the beach, very close to the beach in Haifa.
So an urban environment.
It's I don't know exactly an urban. It's sort of it's very different than when I look at it now than when I look at it as a kid. As a child, it was heaven. Heaven, yeah, because I remember. I think probably till the age of 15, the only thing I did was either on the beach or play soccer. I mean, that's the only two activities that we were engaged in, and most kids. And it's a small neighborhood. It was not part of an urban thing. You needed to get out, take a bus or something in order to.
So are you, to use an awful word, a nerd? I mean, you're the opposite of a nerd.
No, I was a nerd. I was definitely a nerd. Yeah, even though the beach bum life, I definitely stuck out as a sort of a nerd. I liked studying. I mean, it was not so common.
Your parents did not have to.
No. It's
hammer this.
No. They. My father was, sort of. In different conditions, he would have been an intellectual. In different conditions, he would have been maybe an academic. I don't know. It's very hard to say. But I mean, he was just forced to find a job when he arrived, and then he had a family, and he supported it. And actually, yeah.
Is it a house full of books?
No. It's there were books, definitely. He liked reading. Again, it was a matter of time available. My mother less so. He was definitely interested in puzzles. His job was sort of puzzle solving, more or less, in at least the way he always explained it to me, in fixing the engines of large boats where something goes wrong. I mean, finding out what's wrong. I mean, that was intellectual puzzles, which tests to make and so on. I mean, it's something I can relate to. And in fact, he got me, I'm sure he got me interested in lots of the art or the magic of solving problems. And he definitely gave me Russian books that he had that had puzzles in them or mathematical, definitely that's the earliest memories of connection to math I remember.
Can we speak of your parents' ambitions for you at a certain point?
I don't know in terms of ambition. I think they were, they let us be. They were happy with our, I don't remember any force pushing us in any direction. They are happy with our achievements. And
so in this neighborhood, blue collar near Haifa, what is the quality of education in the local schools?
Pretty low.
Very low.
Pretty low, yeah. So for my high school, the one thing they did, which I guess also my teachers recommended, is that I go to a high school. Haifa is more or less layered economically. It's on a mountain. It's really beautiful. By the beach is the lowest. There was a high school. It's a famous high school, in fact, the Reali High School. In Haifa, which was a semi-private thing that also was a rare thing in Israel. It's still a rare thing in Israel. And it was a good high school, relatively speaking. So, it was good. And in it, there were some excellent teachers. And in particular, I had a math teacher who just came from Russia at the last 2 years of high school, and he was phenomenal.
Was he also, because I've spoken to a number of your colleagues in mathematics and computer who were trained in the Soviet Union or were schooled, and the teaching in mathematics was very rigorous.
It was
Would
very
you say
rigorous.
this was the kind of mathematic training you got?
It was not just rigorous, it was also rigorous, but also inspiring. I mean, he was just, his love, his passion for mathematics. He wrote textbooks in Russia, which I had copies of, even though I couldn't read. He taught me some, but he gave extracurricular classes beyond, So some of us took these and learn about some college material. It was.
You should remember his name. What was
Kaplan.
Kaplan.
Yeah.
And you are how old when you first meet him as a teacher?
He's a junior, and since I was 17.
17.
Yeah.
In the Israeli system, or at least in this school, when do you have to decide on a direction? Or is it decided for you by tests?
No, it's you decide everything yourself, or you consult with friends and family. But in Israel, you don't do these decisions in high school, because after high school you go to the army. So you are going for 3 years of intellectual-less existence.
Right.
Most people, some people, there are some interesting jobs in the army. So you don't make any decisions there. You make decisions when you are 21. You are leaving the army, and then you think what you want to do.
Although, and of course I don't know, but I know that something about the fact that many get their introduction to computers and the ability to work with them in the army. Did that happen to you?
No, it happens a lot more nowadays, not when in my time where computers were young. There's some subset of people that many of them do find themselves later in academia, who go either to work with computers or do some mathematically related work, maybe in intelligence or in some.
Yes, but that was not your case.
No, definitely not my case. I went for a year for the flying course, and then I was kicked out because I didn't fly well enough, and then I was in headquarters.
So the world lost a pilot and won a mathematician.
I don't know, but I don't believe in this kind of.
Anyway, so you completed your army duty,
Yeah.
And you are certainly set on going to university.
Yeah, it was natural because I loved studying. It was clear that I'll continue studying. At the time, a relatively small fraction in Israel went to college. Also in America, it became like sort of a degree you must have. But anyway, I definitely wanted to learn, and I wanted to study mathematics, and my parents thought that maybe I should try computer science because I learned mathematics anyway there, and maybe I'll also have a job when I graduate. So I went there.
Yes.
And it was a great decision, I must say, because I fell into this wonderful...
let me see, you were born in 56, so we are now in the 70s, the mid-70s.
Yeah, 77, I went to college 77.
And you went to the Hebrew University?
No, I went to the Technion.
Technion, okay, a technical, high-level technology university.
The MIT of Israel.
The MIT, okay, the MIT of Israel. At this point, what is the state of computer science? Do they have a department of computer studies?
It was just created. It was very young. We had a class of 40 students. It was a phenomenal class. Many of them are colleagues today, are in academia in the US and in Israel. We had phenomenal teachers there, very inspiring ones, and the ones I tend to, connect more to are the theoreticians.
Right. So were they apparent at that point? I know there's a time when so many people think of computers at this era as programming as opposed to the broader theory and mathematics of it. At Technion, are they already aware and emphasizing the theory?
Yes, and I should probably tell you about the big difference, because maybe you interviewed mainly American computer scientists. Theory in Israel was, within computer science, was always, a bigger part, highly valued. And the reason is that in Israel, computer science evolved from mathematics. Names like, Michael Rabin or Amir Pnueli or Eli Shamir and many others, Shimon Even, who was my teacher at the Technion, they studied mathematics. They were mathematicians who realized this new world, and they came from a tradition of mathematics, and they wanted to create foundations. Of course, there were grand theoreticians here, yes. But in the US, computer science evolved mainly from engineering.
Yes.
When I came to Princeton for my PhD, it was in an electrical engineering department. It was not yet a separate department. But anyway, in most of the United States, computer science evolved from engineering traditions. Right. And there, while theoreticians, existed and were needed and were essential for the development of the field, it was not the same.
So I asked maybe a silly question about intellectual snobbery. Didn't it require a leap of imagination for trained mathematicians to say, now I will devote time to computers? Wasn't this a kind of degradation of pure analysis in their minds?
Well, I don't know about other people exactly how they work with this doing work, inserting qualifications like, is it more supreme or more, I don't see any serious mathematicians think about what they are going to work on in these terms. Of course, you may know some, I don't. Or maybe I ignore this aspect. I'm sure that I don't think it was an issue. I think that the enormous intellectual challenges in understanding what computation is, which we are still facing today, were clear to some of them, and I think that's the reason they chose to do foundations of computer science or theory of computation. Yes.
Do you find a particular mentor at Technion?
The one that inspired me the most was Shimon Even. I took several courses from him. He taught mainly algorithms, and definitely my main influence there. I took other theory courses, and it appealed to me very much to study on. I mean, at the time, because I come from a family that's not academic, I didn't even know, even at the Technion yet, that it was a profession to be a professor. Yes. But I definitely wanted to continue studying, and he encouraged me to apply to universities in the US. And at the time, some of my classmates also did the same, so it was a thing to do.
I understand sometimes the role of the mentor or the guide, if you will, the intellectual guide, is to present problems to a promising young student. Was this done for you at Technion, where you were sent to?
I think we were just, no, there was not special relationship. It was just that the environment I was in, the other students and these very good courses that just proposed, I didn't do any research problems, if that's what you mean. Yes. There was we learned, and there were challenging, problems, and I had no idea what research was until I got into graduate school. I have no idea. I knew I wanted to learn more. That's all I knew. I didn't know about this profession, and I didn't know of academic.
You weren't required to do a thesis?
No, you don't do a thesis. It's a 3-year undergraduate degree.
Okay.
Where we just learned,
So now you go into the uncharted world of academic preparation. You research universities in fields that interest you?
No, I mean, it's amazing because I do talk to students nowadays. It was completely naive. Huh. We knew what the best universities are. I applied to about 10 of them. Mm. I was admitted with a fellowship, which was, of course, essential for me to live, only at Princeton, at Yale. And I asked Shimon Even about, and he said that, in theory, they are more or less equivalent, which were both, they were not the best at the time in theoretical computer science. Now it's a major powerhouse here, but he said they are roughly the same, but Princeton is so much nicer place. So, that's my recommendation.
Another person I interviewed in this series who was Indian thought that he was Harry Potter when he arrived at Princeton from India.
It's a really nice, yeah, we like it, of course. Yeah, we also, my wife and I got married. We met at the Technion, so we came here together. And she went to Rutgers,
So now graduate study. I don't say now you get serious, you have been serious along, but now you must specialize or frame the next stage of your career. How do you do this?
Yeah, I never made any such decisions consciously. I don't know, maybe some people do, but I came here and I took some courses, and there were only two theoreticians at Princeton at the time, Ken Stiglitz, who did optimization, and Dick Lipton, who did more complexity theoretic stuff, which he became my advisor. So this attracted me more, and he's a man of amazing creativity and broad interest. So he was he switched research areas like I don't know. So he moved between areas, and I just moved with him. I learned about various things. He would ask me questions about many of these areas, and I also became interested in lots of things. So I never think of myself as working in one particular area. Maybe I got the bug of being interested in, well, theoretical, so mathematical questions about computing, and that's a very, very broad set.
One day you will be in an institute where you can do and think about anything. But as a graduate student, at least in my experience, the structure of the degree requires you to frame either a specialty or certainly move toward a thesis. So where are you moving?
Yeah, no, that's different. Theory is a chunk. I mean, computer science is so broad, even at the time. The programming languages and, software engineering, and there's compilers and some hardware and networks, even, they didn't exist much. Anyway, people were doing different data structures, databases. Yeah, you chose one of these. I chose theory. This was clear to me that I was going to stay close to mathematics and do. That's the only choice. This is the only. I felt that there was no constraint even then. You did what you liked, and that was, you chose your advisor, and then.
But you can choose, but you also require preparation. Did you find that your mathematical preparation was sufficient for your needs in computer theory?
Never. It was never sufficient because I was a student of computer science also at the Technion. So I have to learn mathematics all my life, and this is great too. But I could have, in terms, if had I known, had I been more conscious, I would take, let's say, an undergraduate degree and probably a graduate degree.
Right.
In mathematics, theory of computation has become much more sophisticated mathematically with time, and requires more and more deeper and wider mathematics. So the connections are extremely, interesting and broad. Since I didn't have this background, lots of it I had to do later, which is fine. Yeah.
Again, it may be too broad a question, but we are now in the late 70s?
80, early 80s. I was here 80 to 83.
Okay.
Yeah.
Is it possible to give me a kind of snapshot of the state of computer theory at this point? I mean, what is it like? What are the questions being asked?
Okay, so there's absolutely amazing time because first in the 70s, two major things happened in the 70s, one after the other. One was framing of the question of P and NP, which is the biggest question. I can explain it in depth, but I want to say what the two things are. So,
yes.
These are basic computational complexity questions, which natural things we cannot solve, and which we can. And this was framed mathematically in the 70s, and soon after, and very related to this, was a framework for complexity-based cryptography, which is, again, I can explain. So people understood already since Turing's time that there are certain computational tasks that cannot be performed. They're just impossible to perform. This, in particular, debugging programs is impossible. So that's a very nice beginning to the field. And then people realize that the definition that can be solved is too lax. If it's just solved in finite time is not enough. We need to see the results tomorrow. So people started to investigate time bounds and in general complexity bounds on programs, on algorithms, and wanted them to be really quickly. So this complexity theory was initiated in the 60s. And in the 70s, both in the US and in Russia, people understood that there's a particular class of problems that are extremely natural. We can hope to solve them quickly. Solve them quickly we call P for polynomial time, but it doesn't matter. There's a class we knew how to solve, and this is what more or less related to having computers do it fast. It's theoretical, but it's related to real efficiency in the real world. All the applications you see are, programs that are in P. Yeah, problems that are in P. And there's a larger set of questions that is called NP, whose characteristic is that, maybe a crossword puzzle or a Sudoku or maybe an engineering task. These are things that it's very easy to recognize a good solution when you see one, but maybe finding one, solving such a New York Times may be hard. But if I give you the solution, so anyway, that's NP. That's a class of problems that where solutions can be easily recognized as good, quickly recognized as good, but there are search problems. So can you solve all of these? These characterize more or less all the problems that people are looking at. In almost all of them, a solution, if found, is recognized as good. In particular, mathematical theorems have this nature, right? I mean, maybe it's difficult to prove some of them, but in most cases, somebody proves a theorem, then most mathematicians, maybe with some background, can verify that. Right. This is a good example. So if P equals NP in our language, then you don't need mathematicians. Right. You can automate all of this. This is the biggest, so this since the 70s, that's the biggest question, which is still open. It's one of the clay problems, it's one of the major problems in mathematics as well. But the idea that some problems of this nature are difficult or maybe difficult.
Not susceptible to.
They cannot be solved quickly. They will have to, all these problems have brute force solutions, The proof of the theorem will take 100 pages. Let's try all 100 pages manuscripts. One of them will, let's run through them all. This is the only type of algorithm we know for general problems in NP so far. So, but the idea that there may be problems of this nature that are hard drove another set of people. Started with Diffie and Hellman, and then RSA, Rivest, Shamir, and Adelman, and Goldwasser and Micali to develop a theory of cryptography, which is based on the idea that what is hiding a secret is the computational difficulty of a problem. This idea, which is amazing in itself, is what really caused the internet to be built. Right? Suddenly, with this idea, you could have people who never talked with each other before communicate in secrecy. I think people don't realize so much the fact that cryptography before that, in the, let's say, 3,000 years it existed, was secret communication between people based on the fact that they had secret communication before. So, right?
Yes.
So, in some sense, James Bond has to meet with M before This allowed the situation that you and I, who never met before, or Amazon and I, who never met before, I can send them my credit card number, even though we didn't agree on secret book and secret page and secret.
Right.
Yeah. So it's all based, again, something that I can explain, but it's based on computational difficulty of certain problems in NP that people imagined, like integer factoring. People imagine may be difficult. And
so difficulty becomes a benefit.
Exactly, which is extremely rare thing. It's good to have hard problems. It's amazing, it's shocking, it's surprising, and there are other aspects of this. There are other benefits of hard problems that emerge in the history of computation. With hard problems, you can build good pseudo-random generators. So that's another very important aspect of the.
So are you now jumping into this pool of complexity?
I'm jumping it's the biggest feast of my life, which is still continuing. It's extremely rich and lively with people with amazing talent, extremely creative people. Cryptography at the time, this mid-80s, I went to Berkeley on a postdoc. And so I did a little on my PhD, but I went to Berkeley as a postdoc. And this was sort of the hub or the place where most of the ideas and some of the people, resided or were graduate students at Blum and Goldwasser and Mikali and Yao and so on. There was it was like playing amazing games. Can you do this impossible task?
Yes.
So in cryptography, until that time, secret communication was the major thing you had to do. It was a major problem to solve. But now you wanted to solve all sorts of people. Can we exchange secrets? Can we play poker over the telephone? Mm-hmm. Can we, can we, this zero knowledge issue, can I prove to you something? It's sort of the antithesis of mathematics, right? Usually in a mathematical proof, you would like not only to have a correct proof and know that the theorem is correct, but also understand what's going on. I mean, the proof should be revealing, should be. On the other hand, in cryptography, often you want to prove to the other party something, but specifically only that thing. Let's say that you know that the secret number you chose is a product of 2 primes, but you are not willing to reveal which 2 because this will violate your... So the question that was asked was, is it possible to prove theorems without providing the listener or the student or whoever, your colleague, absolutely no detail about the proof, except it's that your proof is correct.
So this is beyond radical in terms of at least mathematical thinking.
It's a very weird concept. What you have to get used to in this world of cryptography is that the computational difficulties, just like you said, changes the rules in some sense. I mean, it's a wonderful axiom. First of all, it seems to hold in real life, the axiom that some problems are difficult. And once you accept this axiom, both that, some problems are extremely hard and we are computationally limited, then suddenly you can do this magical thing. So one of the,
So Avi, to jump into this, what is going to be and what becomes your contribution, ongoing contribution to this discourse?
There are lots of subjects. So at the time when I was a postdoc, we did this. So we proved that every theorem can be proved in what we call zero knowledge. So this is sort of, definitely a highlight. I'm interested in, another is the power of randomness. So understanding, there are lots of, one thing that developed at the time, again, that was extremely powerful is the use of coin tosses in algorithms that, solving problems that we didn't have any means of solving in a deterministic fashion, using randomness to solve them. This was not a new idea. Monte Carlo simulations existed in the 50s, Ulam, von Neumann, and so on. But just sort of the wealth of applications, the wealth of problems people were trying to solve once computers existed. Many were, hit a brick wall unless you used, randomness. And so the obvious theoretical question is this just because we are too stupid to find the deterministic algorithm? It's always better to have something that's totally predictable and is totally correct always. When you are applying randomness, there's always some small chance of error, some very unlikely event with which you produce a wrong answer. This is accepted, but it would be nicer if you could avoid it. So this is a great challenge that I worked on for 30 years. I mean, lots of my papers.
I'm trying to understand. Is an advance being the tolerance for randomness or the recognition of it as a problem that must be solved?
No, I'm talking about the fact that, first of all, even today, lots of problems that are solved on a daily basis are solved using a probabilistic algorithm.
Right.
Why? Because either it's the only one we have or it's more efficient than the counterpart, the deterministic counterpart. That's a fact. In all these algorithms, there is a tiny chance of error. Okay, so a good example from that time is primality testing whether a number is prime or not. A deterministic algorithm, which is somewhat slower, was discovered in the early 2000s, but for 30 years, and this was important for cryptography because you need prime numbers. So we had these algorithms that were fast and delivered the answer correctly with 99.999% probability, as high as you want, but not 100%. So you should ask yourself, suppose that the security of your system or of your electronic commerce environment dependent on the correctness of this assumption that the number you are holding, which is very long, is a prime. Can you achieve it deterministically? This you can ask about every algorithm that is. So that was a challenge. Can we eliminate randomness from algorithms? That was the question. And we know the answer. It's a bit complicated and related to the P versus NP equation, which is another surprise. So we know roughly the following.
Yes.
So oversimplifying.
Of course.
But if an assumption very similar to P different than NP, namely just the assumption that some problems are exponentially hard, some natural problems are exponentially hard, problems we believe are exponentially hard. If that holds, then you can replace every probabilistic algorithm with a deterministic counterpart. So you can eliminate randomness always. So hard problems are useful in a very different way.
Yes.
Yeah, so.
If the interview were longer, I would get you through your career, but of course you do a number of, you go to a number of places, and in the end you wind up back in Princeton, which is a kind of intellectual home for you.
Yes, yeah, it's definitely one of them. I was just here, the main places I was at is here, Berkeley, and the Hebrew University in Jerusalem, where I spent 15 years.
Well, 15 years is worth at least spending a bit of time with, in the sense of how did you find the nature of the discourse? Is discourse so globally framed now in your field that being in the Hebrew University, not in the United States with other, is not an issue? Or are there different emphases in the various academic environments?
I would say that it's really global. Everybody is aware of what everybody is doing, but still, your colleagues and environment matter. And I had fantastic colleagues, fantastic students, which from whom I learn a lot. I learn all the time from all the young people I collaborate with. It was students, graduate students at the Hebrew University. Here it's postdocs because we don't have students. But it was a phenomenal environment, very enriching, has a very good math department. It was a great place to be.
So you might have stayed if not for the opportunity that the Institute provided.
Yeah, it was an opportunity that we decided to test. And my wife is also working here in the computer center, so we both got offers at the same time.
Right.
And we came here as a trial, we decided to give ourselves a couple of years. And we liked it, so we stayed.
At the end of the interview, I want to at least touch on the fact that at this very moment, you're about to come out with a book. It's essentially out.
Yeah, it's out.
Which brings together so much of what you have looked into. Is it possible to explain briefly what the book aims to do?
The book aims to explain just things I understand well, or I think I understand well, in the way that I like to explain it. It is called Mathematics and Computation. It's about this field that I'm at, in which is it's sort of an interesting dichotomy, and people keep asking me whether I'm a mathematician or a computer scientist, and I say I'm both. But it's sort of an interesting existence because the two traditions, the sort of technological tradition, the mathematical tradition, are very different. The technological side is great because it keeps generating, the new technologies, new models, new things to model, new problems, new algorithmic challenges, new whatever. But it's also demanding in terms of, what it's like to produce. It likes applications. On the other hand, this community operates as a mathematical community, at least in the extent that it builds formal models, prove rigorous theorems. This is as you say, the discourse of the field. I think it's great, has been great for the field. I'm just explaining lots of facets of this field in the book, and at the very end I try to explain more globally why this way of thinking, the viewing processes in general, not just computing processes. This is something that's been happening the last 2 or 3 decades. The interactions of my field with biology, economics, physics, you name it, social sciences, is sort of revolutionizing these fields. In many of them, and in many studies of aspects of various processes in nature, let's say, or in the human, or in the, disease, or everything. The computational element, or the understanding of resources that go into processes, I would say, was lacking, and there are many collaborations in which this is exposed, and this is enriching both us and the sciences. So there are lots more happening, and I talk about that. Most of the book is about various fields of, it's a big field, sort of aims in particular to explain how big the field is, what are the major subfields, and what are the major problems they are interested in, what are the major results. And there are no proofs in the...
And in a way, you're very lucky in your life period, because your study to participation is during this burst of exponential growth.
I'm extremely lucky. I consider myself unbelievably lucky to live in this, in exactly this age where it's a young field. It's a young field that's maybe partly accounts for lack of, maybe more traditional fields are more conservative, or it's a very democratic field. It's a very friendly field. It's a field that's very collaborative. It suits my nature. I like to work with people, and definitely it's bursting with intellectual problems and challenges and modeling problems that are not so. People associate somehow modeling questions in mathematics more with applied math, where you try to model, but here modeling is as important as proving theorems. Just finding the right definitions. Let's say in cryptography is a very good example, but there are many other. Just finding the right definitions just try to define what a zero-knowledge proof is.
Yes.
Is a major issue in itself. Anyway, so I consider myself unbelievably lucky. It's a very fantastic existence.
Thank you, Avi.
Okay, thanks.